Records rolling. It is Monday, February 17th. So when I tell you guys last back on Friday, we are going through this debrief.
Good morning, Viera. My name is Max Chinwan, and I'm a member of Bro Kappa.
All right, so yeah, pick up where I left off there. All right, so there's also free response questions that go with this practice exam. That's the other half. You guys know the format of the AP exam you guys are going to get. Right? The first half is multiple choice, which is what we're in the middle of now. The second half are 4 free response questions. So here's my plan: is I think I might be able to finish these today. Thank you, base. Then I'll have you guys do these in class on Tuesday, Wednesday. The purpose of it being in class is so you can get an idea for exactly what the time pacing is. Yeah.
For the FRQs, are they like 2 labs and 2 written out problem solving, or?
Okay. Yeah, they're all written on paper, right? So I think how the format's going to be is when you guys get the AP exam, the multiple choice should all be digital, right? So you just like click on a computer screen, but you're going to handwrite out these 4 free response questions. Okay. Now, you don't actually do any actual labs, right? There's no like actual equipment, right? But one of the FRQs is always do a lab write-up. Yeah. So just in your mind, you say, okay, well, I would use a scale to measure this. I would use a meter stick to measure this. Yeah.
So one is a lab and the 3 of them are just long questions.
Yeah. All right. So it should be 2 of them are worth 7 points each. Here, let me write this down. All right. So so they're going to be 4 FRQs. Okay. 2 of them are 7 points each. And those they give you, I think they recommend, see, is it 15 minutes? Right, I'm going to write 15 minutes. You go back and check that. Okay. And then there are 2 that are 12 points each. And they recommend, see, is it 25 minutes for that? Would that add up? 45, 30, 40. Yeah, it's something like that. It should be pretty close, right? And one of the 12 pointers is one of these lab write-ups. Okay. All right, so you guys can see those. Now, I do actually want to give you guys a head start on one of these efforts because, right, for different, I was debating this for different reasons, right? Because the first FRQ that you guys see tomorrow is actually really, really similar to a recent textbook puzzle that showed up, right? That some of you guys got. Right? You guys remember I had you guys draw numbers out of a bin? Right? Some of you guys may have drawn number 53. You guys see this this tank spraying water right here? Right. Now the FRQ is not exactly this question, but it's really, really similar. Right. So here, let me go over this with you guys. Right. And if you go home and study this, then it'll make you that much more prepared. Right. You guys see how there's the tank of water and there's a hole where the water's spurting out and it's going to projectile and standing somewhere on the ground, stuff like that. Right? Now, the premise of your textbook question is if they tell you the height of the tank up to the point where the hole is, and they tell you how far downrange horizontally this water lands, the stream of water, can you calculate the height of water above the hole? Right, that's say supplying the pressure that would make it land exactly there. Because if it's too shallow, it's not going to land far enough. If it's too deep, it's going to land way too far. Okay, so this is something that you can solve. Right now, this would be a 2-part puzzle. Now, since your textbook would have given you, or since they did give you here's the exact numbers. They gave 1 meter tall here, and they gave 60 centimeters here. Okay, since you know the values on the projectile, I would start with that, and I would work backwards to figure out what's the height of water in the tank. So start with the projectile. Now you guys remember projectiles? Well, there's a vertical component of motion, there's a horizontal component of motion. And they gave you enough information where you can determine what's the speed of the water leaving horizontally, right? And so matches back up to the picture. You can use this height and this distance to measure, to calculate what's the speed this water leaves right here, which is actually exactly a lab that you guys had. You guys remember taking those launchers to the balcony, right? It's the same thing. And this, I mean, look, it's what, like 5 lines here? Gets to that part. Okay.
Zero vertical velocity.
Yeah. It starts off, right. It starts off 0 vertical velocity leaving the hole here because see guys, it's leaving straight horizontal. It's leaving straight horizontal. So this water is not moving up or down at the instant that it leaves the hole. Right? Now, like short time later, it starts moving down. Okay. Right. All right. So that's the setup right here. Okay. That's the first half of your the textbook version of this. Right? Then you have to go back and say, well, how deep would the water be? And this is a Bernoulli principle question. You guys see the full Bernoulli principle set up here? It looks at conservation of energy, except that it's all pressure terms. I have 6 of them. Okay? Now, part of what makes this work is, well, the atmosphere is pushing above here, but don't forget the atmosphere is also pushing in here. So that's going to cancel out. That's why I that one away. Right? Hey guys, what do you think the speed of the water is approximately at the top of the tank? Yeah, it's really close to 0 meters per second. That you can just round that to 0. So that's why this goes away. Okay. And then, well, if you consider this height change right here, then relative to this height change, this would be 0 height position here. I mean, there's no water pressure at the bottom of the tank, right? So that gets rid of that term. It boils down to 2 terms. Okay. Now, what you might notice, guys, rho gh equals 1/2 rho v squared. Okay, the rho cancels. That's the what does the rho stand for again? Density of water. Right there you go. Density of water. Right. Which would be 1,000 kilogram per cubic meter, but doesn't matter because it cancels out anyway. Do you see now? If you did solve for v at this point, suppose you were solving this the other way, and you were solving for v. Okay. Do you guys see the 2 algebra steps you would get to solve for v? What would v? Here, I really want everybody to make this connection. Guys, everybody not looking at their phones. Everybody's looking up here. Right. I really want everybody to see this connection right here. If you got to this line, and suppose you solved for v, what would v be equal to? Square root 2gh. Guys, it's the exact same as Galileo dropping balls off the tower. Look at that. It's the same thing, isn't it? Except now it's a tank full of water, but it's the same solution. Right? Okay. Luke?
On one side of the equation, you cancel out 1/2 PV squared, but on the other side, it doesn't cancel out.
Yeah. Okay. Because it's sort of a conservation of energy type thought process, except of course it's for fluid, so it's Bernoulli. We're going from point A to point B. And my point A, I'm considering to be the top of the tank. My point B, I'm considering to be the bottom. Right? Now, at the top of the tank, the water level is moving so slowly, you can call that 0 meters per second. That's why it cancels out here. Okay. But it's moving really fast at the bottom. But at the bottom, well, at the bottom of the tank, there's no height at that point. That's why this height term goes away at the bottom.
Okay.
Wait, so the square root 2gh, the h stands for height initial, right?
Yeah, which would be this height right here.
So are you finding the top of the tank or just the point that it comes out?
Okay. Right. Because your conservation of energy, didn't you always go from like some point A to some point B? Right. So this is like top of the tank and this is bottom of the tank. Right. So I'm going from this point right here, bam, to this point right here, bam. Right. Going from this initial point to this final point. Okay. Now they both have the same atmospheric pressure on them, basically, so that goes away. Right. But one has a height elevation but no speed, and the other has a speed but no height. All right. Okay. Right. Guys good? All right, so if you get a good look at that, and if you want to be really prepared, then how about I would really recommend taking out a blank piece of paper and see if you guys can solve number 53 from scratch. Yeah, it's not 100% aligned with see tomorrow, but pretty close. All right, so let's switch over to some multiple choice questions.